chelating agent stuff first. Let's say I had two oxalate ligands on there. We'd call them oxalato or oxalato. We changed the name to reflect that it's a ligand. And so if I have two of them on here, actually, I'm going to do this shorthand. Then this is one way we could draw it, just OX. And that would be two adjacent positions here. And the same thing here. OX. And so,
But you were saying that like the oxalate ion doesn't actually look like that because all the bonds to the carbon are actually the same.
no, once, okay, that's a good point here. Once these two attach here, then these will be doubled. As the electrons get all rearranged, and this, until it looks like this. And so this would be correct. I'm just saying the oxalate ion itself would look like this, but once it binds to it, then we have to look like this. So if I have two oxalates, what's the coordination number here? 4, and then two oxalates, would it be bis oxalato or dioxalato? Bis? Actually, bis is not correct. It's di. Why? Because our primary numbering system is going to be di, tri, tetra. And we only go to the secondary numbering system if we've already used the primary numbering system. In this case, we haven't used the primary numbering system because oxalato doesn't have di, tri in the name. Whereas ethylene diamine has di. So we have the primary numbering system already used in the ligand name itself. And therefore, we have to go to the secondary numbering system. But here, we could just use the primary numbering system. So it's just dioxalato. It's confusing, but that's it. How many oxalates do you think we can fit around that metal, max? How many more oxalates can I fit on that metal, do you think? One more? Two more? We're going to max out at 6. So if we max out at 6, then it's just one more. So if we have 3 oxalates on there, then would that be tris or tri? It's going to be tri. That would be the correct answer. All right, next we're going to go to one of the most powerful chelating agents, and that's this EDTA 4-. EDTA 4- is called ethylene diamine tetra acetate ethylene diamine tetraacetate ion. As a ligand, it's called ethylene diamine tetraacetato. But just as a standalone ion, it's this. So let's draw the formula for this ion. First off, what is the ethylene group? CH2, CH2. And then we have two amines. Amine doesn't have to be NH2. Amine just has to be an ammonia derivative. And so we have different amines. Let's talk about this on the side here. And so an amine is just a nitrogen with 3 what we call R groups on here. I'll call this R prime, double prime, triple prime. And the R is just the rest of the mean, you know. And R could be hydrogen or it could be carbon. It can't be like a halide, that wouldn't be in the mean, like fluoride, it wouldn't work. But as long as R is a carbon or hydrogen, then the electronic characteristics of nitrogen are the same, because carbon and hydrogen aren't that different in terms of electronegativity. And so R, the rest of the molecule, is carbon or hydrogen. So what we're going to have here is this. We're going to have nitrogen here as the mean. And this amine is going to be attached to 2 acetate groups. If it's attached to 2 acetate groups, then there's no more room for hydrogen. And so I'll just have a lone pair here. Actually, let me draw the lone pair off to the right side of this, like this. I'll put the lone pair here. Okay, now an acetate, we have 2 acetates on this amine and 2 acetates on the other amine over here. And so in this case, the R groups are all going to be carbons. But it's still going to behave like an amine, again, because the carbons have similar electronegativity. Now the acetate is a CH3COO minus. But what we're going to do is we're going to get rid of one of the hydrogens and bond it to the nitrogen of the amine. And then this one, we're just going to make the COO minus group here. Okay, so that's 2 acetate groups. Again, acetate CH3COO minus, but since we're attaching this, we're going to call it a CH2. Get rid of one of the hydrogens, bond that to nitrogen. That's going to change its electronic environment a little bit. But for the most part, these are going to remain similar. And then on the opposite end, we're going to do the same thing. And so this is going to be CH2COO minus. So when I add up all the formal charges add up to -4. So this is a -4 anion here, EDTA, ethylene diamine tetraacetate ion. So as a ligand, let's take a look. If I have a metal here, metal plus X here, I have a choice. Let's see. Which one would be a stronger base? Actually, you know, both these oxygens are the same in acetate. But what we're going to do is we're not going to worry about the hybrid. We're just going to take this Lewis structure. Taking this Lewis structure, which one would be stronger, the negatively charged oxygen or the neutral oxygen? The negatively charged oxygen. So this one can attack here. Oops. If this one attacks here, could the second oxygen attack also? No, the second oxygen won't be able to attack because it would be too constrained. And the reason it'd be too constrained or too strained would be 4-membered ring. And so even though it looks like both of these can attack, only one can. And that's it. So if this one attacks, can this one attack here? Yes, that one can attack as well. But let's do it in order. here. It doesn't have to go in this order. It can go in any order it wants. So we're going to attack the first one here. And then look down the chain. We have a nitrogen here. Can this nitrogen attack? And the answer is yes. This nitrogen can attack next. So we'll do that. And then we'll just bring this over here and attack it here. Okay, so I'm going to just start drawing this out here. And so I'm going to attach the first oxygen here. How does that ring look to you? It's fine, right? So then what I'm going to do is I'm going to attach the second acetato to this. Let's see. I'll do it down here. Actually, maybe I'll do it across here. I'll do it across here. So on this amine group, I have two acetates, and this attacks here, this attacks here. So this is two acetatos. So far it's tridentate. See that? What about the ethylene group? Well, the ethylene group is attached to the nitrogen here. I'll do this in a different color here. So I'll do the ethylene coming off this nitrogen here. Do it down here. So now I have the ethylene and the diamine attached here. That's okay. This is 1, 2, 3, 4, 5 numbered ring also. I made this bond long, so that carbon isn't hidden behind the branch. Okay, and now this nitrogen here has two acetato groups attached to it. And so let's go ahead and deal with those here. And so this acetato group I'll bring out to the front here. So that's a C, H, H, C, O, O. And then I'll have another acetato group, and I'll just do this other acetato group a different color here. This is going out back. The C, H, C double bond O, O. So when I look at EDTA has 1, 2, 3, 4, 5, 6 binding atoms, making it a hexadentate ligand. It's a hexadentate ligand. So this is something that Werner won the Nobel Prize for. So EDTA is a +4. How many sodiums would I need to balance out the charge? I'd need 4 sodiums. And so this would be sodium EDTA, or sodium ethylene diamine tetraacetate. Right? But the weird thing is that this is like the blob. It's like in the science fiction movies or whatever. It just encapsulates whatever's in the center there. So if I have EDTA like this, which is a 4 minus, I need 4 positive charges, is it going to encapsulate all 4 sodiums? Actually, it doesn't. You know how many sodiums it encapsulates? In reality, this is not the correct way we visualize the structure. You know, if you were thinking of visualizing it like this, it would make 4 sodium ions plus 1 EDTA 4 minus ion. So, you know, sodium salts are soluble. Soluble salts are strong electrolytes. Strong electrolytes ionize. And so this is the expected ionization for this. But a weird thing happened. A weird thing happened was, you know, people expected this to break up into 5 ions, 4 sodiums and 1 EDTA. But it didn't. You know, it broke up only into 4 ions. Why did it break up only into 4 ions? It broke up into 4 ions because of this. One of the EDTAs and one of the sodiums resulted in a structure like this. Sodium still retains its charge as +1. EDTA is a -4. So +1 minus 4 gives us a -3, or 3 minus. So that's kind of what we have here. We would have a sodium stuck right in the center of this. So the metal plus X is just a sodium ion, and it's stuck there. The other sodiums are outside what we call the coordination sphere. And so we'll have 3 sodiums outside. Oops, I should keep track of the charge. Let me erase that. So let's name this ion first before we move on. Here. What's the name of this ion here?
Just sodium, tetraacetate.
Yeah, but for complexes, this is a complex. And so we don't name the metal first in a complex. We name the ligand first. And the name of the ligand? Ethylene, diamine, tetra, acetato. Okay, now we name the metal, which would be sodium or sodiumate. Well, we look at the complex. Is the complex an anion complex or a neutral cation complex? It's an anion complex. If it's an anion complex, we have to add the 8 ending. The 8 means it's an anion complex, which is what we have. So it would have to be sodiumate, not sodium. Uh-huh.
Okay, so you know how in the complexes we refer to silver as argentate?
Yes.
Because that's its like
Right.
Latin name or whatever. Since sodium is like Na, I'm assuming it's based off of some Latin name.
Yes.
So why don't we call it that in a complex?
Yeah, that's better. That's better. So we're not going to call it sodiumate. You know what we're going to call it? You know, sodium is natrium. And so what we're going to do is we're not going to use this name. We're going to call it natriumate or natrate. Just natrate. Although it sounds kind of funny still. But we'll call it natrate rather than sodiumate. But natrium's not on your list though. But you know, you can kind of figure it out based on Na. Na and SO don't make sense. And so that's what we do. Instead of calling it sodiumate, we'll call it natrate. Sodium only has 1 charge, cation charge. What is it? +1, but regardless, we have to add the Roman numeral here. And so we're going to call it natrate 1 or sodiumate 1. Now, this sodium is covalently bound to the ligand. These are covalently bonded atoms. to sodium. It's kind of weird because, you know, metal and non-metal forms ionic bonds, but these aren't ionic bonds, these are covalent bonds. The ionic bonds are going to be out here. So if this were sodium in the center here, then we'd have other sodiums out here to balance out the charge. And how many would we need? We'd need 3 of them. And so the structure ends up being this. Na3 Na EDTA. Yeah. So now when we dissolve this in water, only 3 of the sodiums break off because those 3 sodiums are ionically bonded. And the other sodium does not break off because the other sodium is completely encapsulated by EDTA. And so that would be sodium EDTA 3 minus here. Now, once sodium is completely encapsulated, it's extremely difficult to get out. You know, it's in this cage. How can sodium escape? Because, you know, how probable is a coordinated attack? 6. We got to break 6 bonds at the same time. You think that's likely to happen? No, it's highly unlikely. And so this looks like there's no escape for sodium. You know, it's like in the python grip. Or it's been swallowed up by the blob. It's gone. Or is it gone? Now, there is a way that sodium can escape. Do you know how sodium can escape? So let's say the blob just ate the sodium ion here, but another ion comes by, and the other ion, the blob would rather eat that, but it can only eat 1 ion at a time. So this other ion comes by, it's a calcium ion. A calcium ion comes by, the blob would much prefer the calcium ion, EDTA, than the sodium ion. So can it spit it out? No, it doesn't spit it out. You know what happens? What happens is, you know, parts of this can break off. Let's say this breaks off here, or the oxygen breaks off. If the oxygen breaks off, then you have this acetate group flopping around, right? And so let's say the acetate breaks off and the calcium's right there at the opportune time, and then the oxygen on the acetate group binds to the calcium. And that forms a stronger, because it forms a stronger bond because calcium is what charge? 2+, and sodium is +1. And so what can happen is, okay, that breaks off, then another breaks off, and then another. And so eventually what we're going to have is we're going to have exchange. This is called chemical exchange. And so what we're going to do is we're going to exchange out a sodium for a calcium. Okay, that's fine. And then let's say a lead comes by. A lead 2+ comes by. Do you know what's going to happen? It's going to capture the lead and spit out the calcium because the lead forms stronger coordinate covalent bonds. And that's just a chemical exchange process. And so EDTA, calcium EDTA, with calcium stuck in the center there, is used for treatment of lead poisoning. Because, you know, what's going to happen is eventually it's going to spit out the lead and encapsulate the lead. Spit out the calcium and encapsulate the lead. That's what I meant. Uh-huh.
What causes them to form those stronger bonds? Those coordinate.
That would be like hard, soft acid-base theory. You would look into that. You know. But we can come up with some simple rankings. Things that form stronger bonds, things that form weaker bonds. And we'll talk about the ranking here. Like the higher the charge, cation, the better. You know, so that's one. And so Lewis acid-base strength. This is the entire universe, but what we're going to do is we're going to narrow the universe down to complexes. And so this just applies for complexes.
And so this chemical exchange process doesn't require any type of catalyst, it's just...
No, it doesn't require catalyst. Although, you know, if you have heat, that's better because then you increase the population of higher energy. It just requires a population of high energy. What you need is a big collision to knock off the ligand atom. And at room temperature, the population's kind of small, but at higher temperatures it's bigger. So you're going to have faster chemical exchange processes at higher temperature. But if you had a catalyst, yeah, that you'll have to take a look at more case by case. But higher charge typically is more acidic. And then for the ligands, we have this. The carbon donors are going to be the strongest. And so we're going to go from strongest to weakest. The carbon donors would have a lone pair and a negative formal charge. And so could you have 3 single bonds? We'll call R, R, R. And the R's don't have to be the same. So R, double pine, whatever. Or we could have a double bond and a single. And a lone pair here. Or we might have a triple bond to one R group here. And so the carbon donors are the strongest. So examples of this would be carbon monoxide, cyanide. Those are very strong. And then we follow that by nitrogen donors. The nitrogen donors would be like amines or ammonia. That is a nitrogen with 3 R groups. The R would have to be carbon or hydrogen. If it's like chlorine or fluorine, it changes the characteristics totally. And so we could have 3 single bonds, or we could have 1 double and 1 single. Or we could have triple. Here. Okay, going weaker here. Going weaker, then we have the oxygen donor. I can't scroll to the right for some reason. The oxygen donor could be a neutral oxygen, like a bridging oxygen, so we'd have 2 R's. If R were hydrogen, then this would be water. Or we could have a terminal oxygen like this. And so we could have a bridging oxygen, which would be water-like, or terminal oxygen, which would be hydroxide-like. You know, if R were H, it would be hydroxide. If R is carbon, it'd be very similar. Like, for example, if R is methyl, we'd have methoxide. Methoxide's a powerful base. And then we have the halides. Halides aren't that great, so like chloride, even though it has lots of lone pairs and a negative charge, it's not that great. Fluoride, bromide, etc. These are the weaker, or weakest. And so looking at these bonds here, you know, I'd expect it to be easier to break the oxygen metal bond because oxygen is not as good of a donor as nitrogen. These bonds should be stronger, the ones with nitrogen.
For example, like with the higher temperature, those like bonds are more likely to break. What do you mean by like the population increases with temperature?
What I mean by that is the population of high energy. Let me see here.
Oh, okay, I see.
Yeah. So just to, well, let me just do a quick example of this. You know, it depends on how strong the bond is. If the bond is this strong, and we're at this temperature, red temperature, then nothing's going to break, you know. But at the blue temperature, then we're going to get some breakage occur. But if the bond is this strong, you know, then everything, it's going to be breaking all the time. We have names for that. When the bond is very strong, we call it inert. So, for example, cyanide bonding to hemoglobin is inert. It's very hard to break off. It's like this, and it's not going to break off. But O2, oxygen bonding to hemoglobin, is what we call labile. Labile means it's easy to break off. Super easy to break off. Speaking of O2, is O2 a monodentate or bidentate ligand? I'm sorry? It would be monodentate. Why couldn't it be bidentate? Well, first off, O2, this is the wrong way of thinking about it, but remember, for ligands, we're just going to go ahead and use valence bond. It looks like O2 could be bidentate. Doesn't it? Shouldn't it be bidentate? It's not stable bidentate. It's not going to be stable because it's going to form what membered ring? Three-membered ring. Three-membered ring is 60-degree angle. And if you treat if you treat these as sp2 hybridization, that's going to be like 120. This is going to be awful. Awfully unstable. And so oxygen is going to be a monodentate ligand, not a bidentate ligand. So this is all part of, all part of this. One way we could just memorize it, memorize all the ligands, but that's too much. So what we do is we try to look for patterns, trends, based on more of a theoretical. The theoretical comes from understanding the structure of these as much as possible. Now, I'm going to move on from this to the homework. Oops, that's not. So there are some more questions about the homework. Let's get those answered and then come back. So the question was, what's the correct answers for the number 4? Question number 4. Oops, that's not what I want there either. Question number 4. All right, let's just go through all of these. What's this one called? Diamine with 2 M's or 1 M? 2 M's. Diamine. Silver or arginium or argentate. Silver, this is a cation complex because we have an anion here. So diamine, silver, what's the charge on silver? Well, ammonia is 0, so silver must be +1 in order to balance out this. And we know silver is usually +1, so this is diamine, silver 1 chloride. Diamine, silver 1 is all one word, and then space chloride. Let's see if they have that in here. Yeah, this is correct. Diamine, silver 1, no spaces, space chloride. This one we already talked about, correct? But this is how I'd like you to name it. I'd like you to write the formula in alphabetical order and name it in alphabetical order. So what I would have done is I would have flipped these. And so the mean would have come first in the formula and followed by the aqua. We're going to do everything alphabetically according to the name, which is one of the set of rules. There's some conflict between the rules. Everybody wants their set of rules adopted. And so this lack of cohesion in the rules means I'm not going to be very strict on this. But let's see what the book did. I should make these boxes a little bit bigger. They call this tetramine diaqua sulfate. Yeah, I would have named it the same. Tetramine diaqua sulfate, or tetramine. You could get rid of one of the vowels. This one, chloro or ethylene diamine comes first. Chloro, dichloro, ethylene diamine. All right, so they're going back. Sometimes they use chloro, sometimes they use chlorido. So here, dichlorido, and this is wrong. 1,2-ethane diamine. The book didn't even talk about this. And this is dichlorido, ethylene diamine, platinum 2. That's correct. How about this one here? Okay, bromo versus aqua. So I would have done this. They're doing it based on the formula. You could do it that way. It's fine. If you do it that way, I don't care. So whatever you feel comfortable with. If you like this method, just go ahead and do it. So B comes before H. And so you write B, or it's based on the formula. But when we name it based on the name. And so here, bromo versus aqua, which one's going to come first? Aqua. So this is going to be penta-aqua, bromo or bromido, chromium. And now the charge, this is +2, this is -1, this is 0. So this has got to be +3. +3 minus 1 gives us +2. And so it's going to be chromium 3. Roman numeral 3. And so let's see. Yeah, they did penta-aqua. A comes before B, bromido, chromium 3. I would have written the formula in this order too. So I don't care which way you do it.
Professor, what's the rule for double vowels, did you say?
The double vowels, you could leave it or you can remove it, but it depends on the flow of the name, you know. And so if it flows better without the double vowel, then just go ahead. Like carbon monoxide or carbon monoxide, you know. And so it depends. Nobody calls it carbon monoxide. Everybody calls it carbon monoxide. And so it's just the flow of things. Whereas other things, penta-aqua or pentaqua. So penta-aqua, well, maybe penta-aqua, you know, makes it clearer than pentaqua or pentaqua or something like that. Which one? The answer that I just showed you here? It's okay. Don't frustrate yourself with this. This is the only assignment that's going to be screwed up like this, I hope. So just do this. Just do it. Try it, you know. Put it in, and don't worry about repeated attempts. I'll just correct it. In fact, if you just try one answer on each of these, then you'll get full credit in this. I give up on this. Okay, the catine's easy. That's rubidium, which is a +1 cation. So this is rubidium. The anine's a complex anion. So what do we name this complex anion? Tetrafluoro or tetrafluorido, silverate or argentate or silver? Argentate. And the charge on silver? Now this charge is really screwed up because rubidium is a +1, and that means fluoride is what? -1. So -1, that means silver has to be a +3. Have you seen silver +3? No, me too. I haven't seen silver +3 yet. I have to look at that one, make sure this is not an error. Gold, yes. So if that were gold, no problem. Gold +3, but silver, this is very unusual. This throws up a flag for me. But it's all right. We name it as it's written. So rubidium tetrafluorido, argentate 3. We write a Roman numeral for everything. Let me tell you, one of the reasons we write a Roman numeral for everything is because sometimes the metal has a 0 charge. And so what's a Roman numeral 0? Can somebody tell me what Roman numeral 0 looks like? No idea? Me too. I have no idea. So we're just going to write a 0 in parentheses. That's if there's zero charge.
Isn't the concept of zero started in like India or something?
Yeah, it's like in Hindu-Arabic numbers. So
Yeah, I'm not sure. I'm not sure the history of that, but that's. All right, here's another anion complex. This is going to be sodium. We don't say disodium because if it's an ionic compound, we can figure out how many sodiums we need. So this is just sodium, and what's the name of this anion? So we have cyanido, and what's this? I call this nitrosyl, like carbonyl, nitrosyl. Your book doesn't call it nitrosyl. They call it, what do they call it? Nitrogen 2 oxide? Well, let's see. This is the way I'd name it. I'd call it sodium. Okay, cyano versus nitro. Cyano would go first. So pentacyanide, nitrosyl, iron, and this whole thing's negatively charged. And so it's going to be -2 to balance out the +2 over here. So this is -5 plus 3. So this has got to be ferrate 3. Ferrate 3, because it's an anion complex. Let's see what they called it here. Sodium pentacyanide, oxido nitrogen, ferrate 3. And so rather than calling it nitrosyl, they call it oxido nitrogen. I don't like oxido nitrogen because nitrogen could be a ligand too, and oxide can be a ligand as well. But that's it. So that's number 4. So number 4, I didn't realize that number 4 posed so many problems. And the other one that I got some questions on was number 63. So let's take a look at number 63. This is platinum. Platinum can be attacked by ammonia or chloride. Amines or chloridos or chloros. What's a better base? Nitrogen donor or halide donor? Nitrogen. So if there is a competition between amine and chloro, amine wins. So this Alfred Werner won the Nobel Prize for his work on the structures of these complexes because certain things weren't known. So like this here, you know, previously chemists would think like this: 4 sodiums, 1 EDTA, then it's going to ionize like this: 4 sodium ions, 1 EDTA, 5 ions. But they didn't know about these complexes like this. And so we only end up with 3 sodiums. And that's going to change its electrical conductivity. You know, the more ions we have, the greater the electrical conductivity. So our deionized water should have 0 ions, so it should have 0 electrical conductivity. And we test our DI water using an ohm meter. Ohm meter measures electrical conductivity. Right? In fact, it measures electrical resistance. So what we're looking for is infinite resistance. And we know our water's gone bad when our water starts to conduct electricity, because tap water does conduct electricity. It conducts electricity quite well because there's a lot of ions in there. And so, so here, these 2 species would have different electrical conductivities, and based on the different electrical conductivities, we could determine if we have 5 ions in solution or 4 ions in solution, because 5 ions is going to give you a greater electrical conductivity per mole than 4 ions in solution. And so the last homework problem is this. This molar conductivity is electrical conductivity per mole, on a per mole basis. So the number of ammonia ligands, if we have 6 ammonia ligands, that gives us the highest electrical conductivity. As we increase the number of ammonia ligands, the electrical conductivity drops to 0, and then it increases again beyond 2 here. And so what they want us to do is they just want us to write out the structures of these. So let me show you what they're asking for here. And this is going to be platinum. 4. It turns out that platinum 4 complexes are octahedral. And so this would be based on the homework here. What time do you go till? 4:20? Okay. 4:40? 4:20?
Got like a little over 3 minutes.
Okay. Thanks. If we have no ammonia ligands, maybe we'd expect something like this, correct? But what's a better ligand, chloro or aqua? Aqua. Actually, I didn't answer this correctly because I didn't look at the chart they had there. I didn't know they were looking at these. If I have an aqua come along here, you know there's going to be an exchange here. And so what's going to happen is there's going to be a collision, and the aqua is going to come over and knock off the chloride. And so the aqua is preferred. And so what we end up with is we're going to exchange all those chlorides for aquas. And these waters are strange because these waters are going to be coordinate covalently bonded or covalently bonded to the platinum. All right, this is platinum plus 4, so this whole thing is going to carry a charge of what? Plus 4. That means in order to make a neutral compound, we need 1, 2, 3, 4 chlorides around this, to surround this. And so this is going to be PT, H2O, 6, plus 4, and Cl4. So when we dissolve this in water, it's going to look like this. Something like that. All right, but it's complicated because sometimes the chloroligands are going to be on there, chloroligands. And so we could see. And so let's take a look at what they're asking us to write. That's not what I want. So part A, write the formula for a coordination compound corresponding to 0 ammonia ligands. 0 ammonia ligands here. So if we have 0 ammonia ligands, write the formula for the coordination compound corresponding to 1 ammonia ligand, and then 2 ammonia ligands, 3 ammonia ligands, 4 ammonia ligands, etc. And the graph below represents the molar conductivity, and then we just look at ammonia and chlorido ions, and maybe we're going to ignore the water ions. And so let's look at part A. Let me see if they're ignoring the water or they're factoring in the water. So I'm going to go and take a look at what they're doing. They're ignoring the water ligands. And so let me redo this. So here we're going to go with this. We're going to ignore the aqua ligands. So let me redo it here. And that happens with aqua. Aqua is it depends on how easy it is to break off. It might not be as strong as attacking, but things get complicated because we have to use HSAB to completely analyze these. And so if there's no ammonia ligands, then we end up with this. Platinum is plus 4, and then we have 6 chlorides. So that's plus 4 minus 6 gives us minus 2. And to balance out the charge, we're going to need 2 potassiums. So we're going to get K2, PT, Cl6, there. Okay. And so when this one dissolves in water, we're going to form 2 potassium ions and 1 of these. Now the chlorides aren't going to break off because the chlorides are covalently bonded. There is a chance they could break off through collisions and whatnot, but for the most part, we're just going to say it's stuck on there. That's going to be 2 minus. So this is part A. Part B, we're going to have 1 ammonia ligand. And so we're going to have PT. Now, I'm just going to do this alphabetically, not based on, if we did it based on maybe we should do it based on the formula here. If I do it based on the formula, I'm going to get Cl5NH3. C comes before N. If I do it based on the name, I'll get PTNH3. Amine comes before chloro. All you need to know is that the rules are all mixed up. So I don't care which way you do it. You could do it amine and chloro or chlorido, or you could do it C versus N. Okay, but what's the charge on this complex going to be? -1. And so that means it's going to be K, PT, I'll just do it my way, Cl5NH3. And so when we dissolve this in water, potassium salts are soluble salts are strong electrolytes, so we're going to form 2 ions. The chlorides here are covalently bonded, and the ammonia is covalently bonded. And the ammonia doesn't carry a charge anyway, so we end up with 2 ions. And so its electrical conductivity should go down. Part C, we're going to throw 2 amines on there. So I'm going to do it this way too. Amine, actually, let's do it my way. NH3. I don't know if I did it my way the last one. 2 NH3s and then 4 CLs. That adds up to a coordination number of 6. These are all monodentate ligands. Platinum's +4, chlorine's -4. This is all covalently bonded. So when we dissolve in water, nothing happens. This would be a non-electrolyte. It's molecular. Covalently bonded molecule. Just ionic bonds would break off, so no chlorines would break off here. And so we expect this to be a non-conductor. Part D, we'll go with 3. So this is going to be PT, NH3, amine first, 3, Cl3. What's the charge on this one? Plus. And so this is going to form the compound PT, NH3, 3, Cl3, chloride. Now this is funny here because I have a total of 4 chlorides. So the early chemists would think all 4 chlorides would break off. And so pre-Werner, this is post-Werner, this is Werner won the Nobel Prize for this. Pre-Werner, chemists would have written it like this. Chemists would have written it, this is platinum 4 chloride, dot 3 NH3s. The ammonias would act like hydrates. You know, water is a hydrate, except it's ammonia. Ammonia is very polar, like water, so it can get stuck in the crystal lattice. It gets stuck in interstitial sites, you know, where you have holes. And so we have a platinum 4 chloride lattice with ammonia stuck in the holes of the lattice. like moisture can get stuck in the holes of the lattice. But when you dissolve this, this is what we should have formed. Pre-Werner, people thought, okay, this is just like a hydrate. And so when you dissolve it, you should form platinum 4 plus 4 chlorides plus 3 ammonias. And it breaks apart the lattice, frees up everything. You break apart the lattice, frees up everything, and then we get 5 ions that can conduct, and then this doesn't conduct electricity much, unless you look at the hydrolysis product of ammonium. Post-Werner, it doesn't break up like that. Post-Werner, how many ions does this break up into? Just 2. Because 3 of the chlorides are covalently bonded to platinum. Only 1 chloride is ionically bonded, and that would be the one out here. And so the electrical conductivity is dramatically different. And so what they saw is just weird electrical conductivity and weird reactivity. In Werner's times, they didn't use electrical conductivity. In Werner's times, they analyzed the chloride content by precipitating it with silver nitrate. And here we expect 4 moles of silver chloride for every mole of this. But they only ended up getting 1 mole of silver chloride. And so the discrepancy had to be resolved. And the discrepancy was because they were looking at the structure wrong. And so the stuff inside the complex is covalently bonded and doesn't ionize. Okay. All right, so that's a start for the last problem there. So just continue with that. Now, I'm going to, my Excel has crashed, so I'm going to switch to Word. Right now. I need to get into chapter 16, so I don't fall too far behind. So we're going to just take a peek into chapter 16, which is chemical equilibrium. Equilibrium is singular, equilibria is plural, so I'll just call it chemical equilibria. In other words, what we're looking at here is Chem 1b stoichiometry. When we do Chem 1b stoichiometry, we set up, we use the ICE method for that. And we set up an ICE table. ICE table is, we have I for initial. And so let's look at a reaction here. I'm going to look at this reaction. It's going to be the reaction of sodium hydroxide plus hydrochloric acid. Sodium hydroxide plus hydrochloric acid produces what? Yeah, salt and water. So NaCl plus H2O. Initially, I'm going to keep this simple. So I'm going to go with let's go with 0.100 moles of sodium hydroxide. And then over here, I'm going to put 0.150 moles of HCl. And over here, I'm going to put 0 moles of sodium chloride. Over here, this is water. We already have lots of water. So if I leave this blank, if the state is blank, that means it's aqueous. And so the water, there's lots of water there to begin with. So I don't know how much initial water I have. Well, I have lots of initial water. So I'm just going to say 0 added water. Okay, C stands for change. And so what's the limiting reagent here? Sodium hydroxide or HCl? Sodium hydroxide. So there's a driving force for this. The driving force is stronger to weaker, so we expect this to go and completely neutralize it. So we're going to lose all sodium hydroxide.
Should it be moles or should it be molarity?
I'm going to do moles here just to keep it simple. We'll talk about molarity later. But we'll talk about the origin of molarity. But moles is simple. We'll just do moles. And then over here, you can tell if I lose 0.100 moles of sodium hydroxide, how much HCl am I going to lose? It's a 1-to-1 mole ratio. I'm going to lose the same, 0.100 moles of HCl. So at the end of this is the end or equilibrium. You know, the equilibrium state is the final state, EQ. It's the final state here. How much sodium hydroxide am I going to have left over? 0 moles. I consume all of it. How much HCl will I have? I'm going to have 0.050 moles left over. And how much sodium chloride will I generate? So this is all 1-to-1 mole ratio, so this is going to be plus 100 moles. In other words, we look at it like this. This is going to be minus X moles, minus X moles, plus X moles, and plus X moles. So, so what I'm going to have is I'm going to have plus 0.100 moles here. And so the sodium chloride, I'm going to end up with 0.100 moles theoretical yield of sodium chloride. And water, I have to add this 0.100. So it's going to be the initial, whatever I had in there, probably lots, plus 0.100. So I'm going to get a little bit more water that forms in there. But do you ever measure how many moles of water you have? Let's say you have salt water. We care about how many moles of sodium chloride there is, but do you care how many moles of water there is? Not really.
So we just ignore the water in general?
Yeah, we kind of ignore the water, right? So anyway, this is Chem 1A stoichiometry done in Chem 1B style. So the limiting reagent is completely consumed. We end up with nothing left over. There's going to be some excess reagent left over, 0.050 moles. And we're going to form a theoretical yield of 0.100 moles of sodium chloride. So in Chem 1A, we have two scenarios that come up. In Chem 1A, we either have a driving force. If there's a driving force, then we assume 100% reaction. If there's no driving force present, then we assume no reaction. But in Chem 1B, we're going to do things that have partial reactions. So Chem 1B, we're going to look at these reactions here plus others. So we're going to add partial reactions. To stoichiometry. And so an example of this would be ammonia plus water. Ammonia plus water yields what? Ammonium hydroxide. So ammonium and hydroxide here. Let's take a look at the driving force for this. Ammonia is what we call our base. Water is going to be our acid here. Water is amphoteric. So H2O is amphoteric or amphiphilic. Do you know what that means? I'd like to say just amphoteric. It means it could either be an acid or a base. And how it behaves depends on what you react it with. And so ammonia is a decent base. So water is going to act as the acid. This is a Bronsted acid-base reaction in which water donates a proton to ammonia. When it does that, then the lone pair is taken up, here. In other words, we can think of it as Lewis 2. The lone pair attacks the proton, plucks it off, forms ammonium, and we're left with hydroxide. And so ammonium is this. We think of reactions as being two ways, competition. And this will be our base. And so when we look at our driving force, we look at the thermodynamic stability of this. The weaker it is, the more stable it is. The stronger it is, the less stable it is. And so when we compare ammonia versus hydroxide, which one's a stronger base, ammonia or hydroxide? hydroxide stronger, ammonia is weaker. So we'll call that weak W base, and we'll call this S strong base, which it is a strong base. And the same thing for the acid. Water versus ammonium. Water is a weaker, ammonium is a stronger. And so when we look at this is no reaction. We need to go stronger to weaker. And so no reaction, NR. Because there's no driving force. But we know that's not accurate. That's not accurate because we know that one of the this is a chemical property I had to memorize as a student. I had to memorize the chemical property of ammonia. One chemical property of ammonia is that aqueous ammonia precipitates metal cations as hydroxides. So I remember that. And so one of the chemical properties is if you mix aqueous ammonia with metal ions, you can precipitate out the insoluble hydroxides. What are the insoluble hydroxides? Well, the easiest way to remember the insoluble hydroxides is to remember the soluble hydroxides. So what are the soluble hydroxides? Group 1, not all of group 2. Group 1, ammonium and calcium, strontium, barium. And those soluble metal hydroxides are also the strong bases. We'll talk more about it. Do you know the 7 common strong acids?
Hydrochloric, hydrobromic,
Perchloric, sulfuric.
Nitric. Did you get chloric acid? Perchloric acid? Yeah, okay, then you got it. And then we want to know, we want to know all the strong bases. Do you know we have the soluble hydroxides are strong bases? So if we know the soluble hydroxides, we know the weak bases too, like iron 3 hydroxide. Iron 3 hydroxide, weak base or strong base? Well, it's an insoluble hydroxide, so it's a weak base. Magnesium hydroxide. Magnesium hydroxide, weak base or strong base? It's an insoluble hydroxide.
Oh, is it?
Yeah. Calcium is soluble. Calcium, strontium, barium. Magnesium is weak. Magnesium, people eat that. Do you know people eat magnesium hydroxide? Do you know what they call it?
I'll put soup or something.
It's kind of a pasty liquid. It doesn't taste very good. Milk of magnesia. So people eat that. Milk of magnesia. Drink, eat, something like that. But do people eat sodium hydroxide? No, people don't eat sodium hydroxide. Magnesium hydroxide is a weak base. Sodium hydroxide is a strong base. Sodium hydroxide is soluble. Magnesium hydroxide is insoluble. So, sodium hydroxide is also known as lye or drain cleaner. So you don't want to eat that, sure. But anyway, getting back to this, the driving force is reversed. But we know that ammonia is a weak base. Weak bases are weak electrolytes. Weak electrolytes partially hydrolyze water. So there's partial reaction here. And so what's happening is the downhill direction is reversed. So when we look at ammonia and water is down here. And ammonium and hydroxide is way up here. So what we're doing is we're going from weaker to stronger thermodynamically in terms of energy. So the driving force is going backwards. Backwards is downhill. So we can go from higher energy to lower energy. Going forward is not favorable, right? But it depends on how big this hill is. So if the hill, let's say it's like this. This is the analogy I'm going to use. And this is, let's say we're on a bike trip and there are a whole bunch of bicyclists here. And all the bicyclists are stopped at the base of this hill. And then you go, okay, that hill looks impossible. And therefore, we shouldn't climb it. We should stay down here at the base where it's safe. Do you think everybody's going to stay down there? No, because unless they're clones of each other. If they're clones of each other, then everybody would stay down here. But we know that everybody's not a clone of each other. In fact, we're going to have a distribution. This is the diversity part. The diversity part is the distribution. The distribution of what? Of energies. Right? And so this distribution of energies means that even though a lot of the bicyclists aren't going to climb it, there's going to be a small fraction of the population that's going to go for it. And the small population is going to go for it, and they have enough energy to make it to the top of the hill. And so it turns out that for this scenario, 99.9%, greater than 99.9% stay down here, and less than 0.1% make it to the top. This is based on the Maxwell-Boltzmann type distribution at room temperature. You know, if you change the temperature, it's going to change the population distribution a bit. But, you know, it turns out this tiny fraction of ammonium and hydroxide can do things. You know, how did they measure it? First thing is, how they measured it is they measured the pH. The pH is the power of the hydrogen ion concentration. But it turns out we have something called the POH, which is the power of the hydroxide ion concentration. And there's an interesting relationship between pH and POH. The pH plus the POH have to add up to 14. We'll talk about that later. And so if we know what the pH is, so we measure the pH is 9, let's say, then we know what the POH is, and we can figure out, you know, how many made it to the top. But they don't stay up here, you know, they go down. But just as these go down, 2 more make it up. And so what we end up with is we end up with a situation that we have the forward reaction, the rate, and so forward rate is equal to the reverse rate. And eventually what we have is we reach a state of dynamic equilibrium. Because the people that make it to the top are going to get bored eventually, and they're going to want to go down. And then some of these get bored and they'll want to go up. And so for every 3 that go down, 3 will go up. And then what happens is there's no further change. There's no further net change. So these proportions stay the same. You know, it's going to be fixed ratios here, but it's dynamic in the sense that there's always some going down and some going up. It's just so happens that the numbers are equal up and down. And so that's when we hit the state of equilibrium. Equilibrium means no change. Dynamic means there's change. So there's constant cycling up and down here for this. But we've pretty much reached the end of the reaction. So this is it. It'd be nice to predict. Could you have predicted it's 99.9? No, I mean, that's kind of hard.
Well, you did like the reaction and like tested the species maybe, but not just looking at them.
Yeah, not just looking at that. Like if I gave you something else, would you be able to tell me what it's going to be? Let's see, today's the 24th. Not so easily. And so what we're going to do is we'd like to understand this theoretically, because theoretically it would be a fundamental description of what's going on. If we had a fundamental description of what's going on, then we can predict it. So we might look at the Maxwell-Boltzmann distribution and then just kind of figure it out from there, figure out what the population is of higher energy, and then come up with some kind of correlation here. You know, the correlation would be very simple. We could try to do this theoretically like this. If we do it theoretically like this, let me just show you what I'm talking about. How much time do I have? 1 minute? 5 minutes? Okay. I might try it like this. I might look at the distribution under the curve here. And let's say to make it up the hill requires this much energy. So if I look at this is 99.9% of the area, and this is less than 0.1% of the area. And then I could figure it out that way, correct? And so I could try to do it theoretically, come up with some kind of theoretical correlation. But right now, what I'm going to do is I'm not going to approach it theoretically. What I'm going to do is I'm going to approach it from the other end, experimentally. And so what I want to do is I want to see the observations. And some of the observations are very tricky because it doesn't hold. So the next observation is this. This is for 0.1 molar ammonia. For 0.1 molar, I do this. If I decrease the concentration, a weird thing happens. If I decrease the concentration and make it more and more dilute, then the percentage of the population that makes it to the top increases. However, if I go the opposite way, if I increase the concentration, if you increase the concentration, you're increasing the population here, and you think you get more up here as a percentage, or the percentage would stay flat. But in fact, the percentage decreases. So we see some weird observations with this. Those weird observations make it difficult to predict because the percentage is not fixed. The percentage depends on what your initial concentration is. And so what we need to do is we need to take more observations to see if we can find any patterns in this. And so what I'm going to do is we'll take some data from chapter 16 of our book and then analyze that data here. So I'm going to leave that reaction for right now. We'll come back to that reaction a little bit later. Right now we're going to look at this reaction here. This reaction is going to be 2 copper 2 pluses, aqueous, but I'm not going to write aqueous there, plus a tin 2 plus yields 2 copper plus 1s plus a tin 4 plus. This is an example of a redox reaction. Looking at this redox reaction here, let's see, copper 2 gains electrons or loses electrons. So we go from 2 plus to 1 plus. If we go from 2 plus to 1 plus, that gains electrons, and we call it an oxidizer. Oxidizers take electrons, or oxidizing agent. OA, I call it. What did it take electrons from? It took electrons, must have taken electrons from tin 2. So tin 2 goes from tin 2 to tin 4, so it must have lost electrons. So this is going to be our reducer or reducing agent. Here. So tin 2 loses 2 electrons to go to tin 4. Those 2 electrons go to copper. Copper gains 1 electron each, and so it goes from plus 2 to plus 1. Okay, now all reactions are competition. You know, which direction is downhill? I don't know which direction is downhill. Can you tell me, is forward going downhill or is reverse going downhill? And so when we look at this copper plus is going to be the reducer or the Ra in the reverse direction because going backwards it loses. And tin 4 is going to be the oxidizer or OA in that. And so what we're going to do is we're going to use the chart to determine which way's uphill or which way's downhill. And the chart, we have a good chart in our book in Appendix D. And so let's take a look at the chart from Appendix D of our book. So this chart is hard to get your bearings, but here we can get our bearings here. Because we see on the top left, do you see that? It's F2. And F2 is the most powerful oxidizer on this chart. So F2 takes 2 electrons to form fluoride. And so we're going to go down here until we hit one of our oxidizers. This is from Appendix D. Keep going down, 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 down. I see copper 2 plus here, but I can't use this one because this is copper 2 plus iodide plus an electron. So that doesn't work. So let's keep going down. I see copper plus 1, but I can't use this one either. This is copper plus 1 plus an electron. I have copper plus 2 on the left. So I don't want to use this one here. Okay, I see it here. I see copper plus 2 taking 2 electrons to form copper 0. I can't use this one because it's not going to copper 0. So let's go down further. Okay, now I see it. Here I have copper plus 2 plus 1 electron goes to copper plus 1. Normally, when we have a conflict, we pick the highest one or the strongest. But we can't pick the stronger one because that's going to copper metal. We have to use this one instead. Here. Now we compare the two oxidizing agents. Oops, sorry. The oxidizing agent on the left is copper 2+. The oxidizing agent on the right is tin 4. So which one's stronger? Copper 2+ is stronger than tin 4. And so this is what we're going to have. We're going from copper 2+, which is a stronger oxidizer, S for stronger, okay, to tin 4, which is weaker. So let me just finish off with that. This is driving force here. Okay. All right, so we'll continue this tomorrow. But this is our start for Chem 1B stoichiometry.